Hello, my name is Saurabh Suryavanshi and I'm going to discuss the next generation of devices that will revitalize Moore's law and enable sub-5 nanometer technology. Specifically, I would like to talk about two-dimensional field effect transistors. I would argue that these materials are a strong candidate for sub-5 nanometer technology node. 2D materials are layered materials. They could be semiconducting like MS2, metallic like graphene, or could be insulating like boron nitride. For comparison, I'm drawing silicon which has bonds in all three dimensions as can be seen from the figure. For 2D material, all the bonds are in a single XY plane and there are no dangling bonds. The typical thickness of 2D material is less than 1 nanometer. We can make transistors entirely out of 2D material, or the materials could be combined with current CMOS technology as a replacement to the channel material. Let me take a step back and discuss how these devices are the backbone of technology that we see around us. Today we have plenty of applications that require high performance computing and consumes a lot of power. These applications depend on hardware that is powered by ever improving devices. As we shall see, we need to improve these devices in order to reduce the overall power consumption by the applications that we intend to work with, as well as improve the performance of our applications. Moore's law has enabled reducing device sizes and improvement in performance over last few decades. We have traditionally achieved that by reducing the size of the transistor. With each generation, our aim is to reduce the delay given by CV over I. For smaller devices, the capacitance reduces because the device area is smaller. Smaller devices also have a smaller channel length, so you end up having large current. In order to keep the power constant, we also need to reduce the supply voltage. As can be seen from this graph, industry is using FinFETs for 22 nanometer technology, and as can be seen, and we are going to argue that later, that FinFET is not the best option moving forward and we need to look at emerging technologies as alternative. The number of applications that rely on high performance computing is increasing exponentially. The increasing number of data centers to support this application is causing an overall increase in power consumption. Today, data centers in the US consume about 2% or more than 2% of total power. On the other hand of the spectrum, we have consumer electronics which are portable and are becoming omnipresent in our lives. We need longer battery time and better performance. However, as we increase the transistor speed or the frequency of the transistor and increase the performances, we also end up increasing the power of these transistors. And therefore, our battery lifetime is getting smaller and smaller. Very slow increase in the energy density of the battery is also not helping. As can be seen in the last 2 decades, the energy density of battery has hardly doubled. We have not been able to reduce the supply voltage of these devices, and as a result, we are increasing the current, therefore also increasing the power. Today, the transistors get so hot that we can literally cook an egg over a microprocessor. The maximum power dissipated, or the limit of the maximum power that can be dissipated without reliability concern, is limited by the capacity of the air to remove the heat from the material. This is typically around 100 watts per centimeter square. Incidentally, it also is the power density inside a nuclear reactor. In order to reduce the power dissipation below this limit, which is 100 watts per centimeter square, we had to restrict transistor speed. It is also reflected in the fact that a lot of transistor frequency have saturated to 3 GHz. A key component to reducing power is to reduce the supply voltage. In order to do that, we want higher on current, which implies we want larger injection velocity and larger mobilities. We also want smaller off current, that implies good gate control and smaller subthreshold slope. In the recent past, the mobilities of silicon have been increased by straining the channel material. So increase in mobility in addition to reduction in channel lengths have enabled increasing on current. The off current, on the other hand, were increased by increasing the gate control in FinFETs by allowing the gate on 3 sides of the channel. We can further reduce the off current or reduce the subthreshold slope by reducing the channel width, which will reduce the depletion capacitance. However, as we reduce the channel width, the transport properties of silicon starts to degrade rapidly, as can be seen from this figure. This happens because you end up having more scattering for electrons on the surface of silicon. In addition, because of the quantum confinement, we reduce density of states, which ends up reducing the channel charge and eventually reduces the on current of the devices. As a result, we end up having reliability issues as we go down to smaller channel widths. To compensate for the smaller channel widths, we need to have taller fins, which further affects the reliability by increasing the possibility of fin collapse. Industry has taken a note of it, and a lot of voices in industry claim that FinFET is not the best solution while going forward. Because of the complexity in the fabrication technology involved, Intel has been struggling to have their production on time. Another problem with FinFETs is that because of the 3D design, the capacitance between the gate as well as the source and drain is much larger than what we expect from a linear technology. As a result, the delay for FinFETs are relatively large. The other effects that come into picture for FinFETs include corner effect that come because of sharp corners in silicon which have larger electric field and which further causes reliability concern. When we scale down transistor channel length, the source to drain tunneling starts to become significant and it increases the off current, as can be seen. The tunneling happens because of what we call as band-to-band effect. The band-to-band tunneling increases especially for materials having very small effective mass, which is typically true with 3-5 materials. As a result, even though 3-5 material have large mobility, they are not very suitable for sub-5 nanometer application because of increase in leakage current. So far, we know that from our discussion that ideal transistors should have thin channels to have better gate control and smaller subthreshold slope. It should have good transport properties to have larger on current, and it should have a larger effective mass to have a larger density of states, therefore larger on current, and at the same time have a smaller leakage because of band-to-band tunneling. It turns out that all these properties are very much available in 2D material. They are thin, they have large enough injection velocity, and they have large effective mass. Going to 2D also helped to reduce the fringing capacitance which was dominant in FinFETs. In addition, the possibility of having low temperature processing will enable design of 3D ICs using 2D materials. Our simulations show that 2D material starts to become promising, especially at shorter channel lengths as we expect from our discussion so far. It should be pointed out that the current state of the art technology is pretty far from the projected performance and there is a long way to go. This particular plot was done for low power by fixing the off current for different channel lengths. The competing technology for 2D material, 2D semiconducting material involve graphene, but unfortunately, graphene cannot be used because it has a zero band gap and therefore a very low on-off ratio. Another potential competitor for 2D material involve carbon nanotube, but as can be seen from this figure, it has a very huge variability. This is because of the variability in the chirality of carbon nanotube as well as the variability in the diameter of the carbon nanotube. The variability in this at device level negatively affects system performance. On the other hand, 2D material, even though they are slightly newer technology compared to carbon nanotubes, have a very good ion by IF ratio owing to good gate control. So far I have talked about MOS2 as a potential 2D material. In reality, there are many other materials that are available which are 2D in nature. Depending on composition of this material, we can get different mobilities and different band gaps and different physical properties. Highest mobilities in this material can be in few thousands. Depending on the application that we intend these materials for, we can pick and choose the properties of these materials. Hopefully, I was able to convince that the 2D material are a very strong candidate for sub-5 nanometer technology node. 2D material in principle demonstrate a capability to provide systems that are high performing and small power. At the same time, they can potentially be flexible and transparent because of their monolayer nature. However, this is not a complete picture and I would not bet all my money on 2D materials yet. As always, there is no free lunch. To leverage the benefits of 2D material, we need to have wafer scale growth. The figure here shows wafer scale growth for graphene. We need to grow at least 0.5 nanometer thick material on 300 millimeter diameter of wafer. This is roughly corresponds to growing 5 millimeter material over entire United States of America. This is bound to induce variation as can be seen from a closer look at the growth of MOS2 in our lab. So you can see spots of bilayer as well as some trilayer on the monolayer growth. This is important for 2D material because the properties in 2D material vary strongly with the number of layers. For example, for MOS2, a single layer MOS2 has a band gap about 1.8 electron volt. If we go to 7 layers, the band gap is 1.2 electron volt. The other properties of the material also change according to the number of layers. Another challenge with 2D material is reducing the contact resistance. The current state-of-the-art contact for 2D material is at least 10x of ITRS requirement. As you can see from the figure, there is a van der Waals gap because 2D material do not have dangling bond and they cannot react with materials readily. In addition, because of the thin channel thickness, we have a current crowding and a barrier height because of the difference between the work function of metal and semiconductor. Another challenges for 2D material involve doping, which is stable in room temperature. Doping will also enable choosing a specific threshold voltage according to the application and enabling N-type as well as P-type FETs for design of a CMOS logic. Currently, we are in a state of developing circuits with few transistors like an inverter, and we are a long way to go from here to developing systems that are truly VLSI nature. We also need to understand the physics of these materials and provide a realistic benchmark for the physical properties like injection and current and charge inside these devices. In summary, I talked about 2D material and tried to argue their importance for sub-5 nanometer technology. I also briefly talked about challenges which are important moving forward for development of 2D technology. Considering the importance of the 2D material and their potential impact, both industries as well as academia should potentially invest resources in developing systems out of these materials. And with that, I would like to end my